All right, it's 11:15. I think we'll get started. So remember, your homework number 4 is due today. Make sure you turn that in. It's not very long, but there are some variables to solve. And there's one more equation that you'll need to finish that homework. And so remember, the flavor of the homework and the flavor of the problems in this section is you have to decode the information that you're given, right? When I tell you all combination is by disproportionation and there's no termination by, all termination is by disproportionation and not combination. You need to figure out what that means in terms of the variables. Or when I give you a density of a solvent, you need to decode that in terms of what variables you have available to you to solve the problem. Additionally, if I don't mention something, I think there was one about chain transfer to initiator, or I didn't mention chain transfer to initiator in the homework. You have no information on that term, so you can probably neglect that, right? You can skip that one unless you really want to go look up the chain transfer constants for different initiators. And so section 2 is all about trying to figure out which variables you have and what you have to work with, and then you can try and look for the equations that make sense. And I encourage you again not to use any shortcuts. Don't use abbreviations. Write down all the words, especially as you're practicing and studying. Write down, instead of CT, write down chain transfer agent. Instead of EWG, write down electron withdrawing group, because that helps you practice and helps you remember what all those variables are, because you're going to have an equation sheet with all the variables. I'm not going to tell you what all the variables are. And so rather than just saying, well, I'm looking for square brackets S, you could say, I'm looking for the concentration of solvent. Oh, that's square brackets S. Okay, this is how I go find that. So, again, what we're shooting for in this class is, I know that all of you can plug and chug the equations. They're not very difficult, although, math errors come up, that happens. But what I really want you to realize is how the terminology and how the chemistry relates to the mathematics and why we describe polymer systems that way. Just like this slide right here. So for living anionic polymerization, and remember, this is a special case, you need to be told something about, okay, it's living, or you need to be told that it was initiated with sodium naphthalide, which is our only living initiator right now for anionic polymerization, because the rate of polymerization is proportional to rate constant for propagation, right, Kp, initial initiator concentration, that's what square brackets I0 means, and monomer concentration. So the rate, how does the rate change as a function of time? So we have an initial rate, right? Because we can put M0 in there. But what's happening is we run a polymerization. What's changing in this equation when we make a polymer? Go ahead.
Monomer concentration.
Yeah, what's happening to the monomer concentration? Going down, right? Yeah, good. So square brackets M, the monomer concentration is going down as a function of time, which means the rate is going down as a function of time. So just because we're drawing straight lines on the graphs, this plot here has nothing to do with the rate of polymerization, so don't get confused about that. But what we're plotting in this plot is X bar N, or the number average degree of polymerization. And now that's proportional to the initial monomer concentration and inversely proportional to the initial initiator concentration. And we don't have any other values for K, so you could just assume K equals 2 if we're doing living anionic polymerization in this class. If K is not 2, I will tell you about that, but you can assume that K is 2 for now. And then we haven't had conversion in our expression for degree of polymerization yet in the addition part, right? We had it in the step growth part, but now we have this nice linear relationship between X bar N and conversion. And this plot right here is a signature for living polymerization. So if you're not sure that it's living, you can make this plot. You can plot the molecular weight as a function of conversion. And if it's linear, your hypothesis is that this is a living polymerization. And so this is a real important signature that you should be able to recognize for the exam, how these characteristic plots look for different polymerization mechanisms. So you'll have to remember step growth, right? I'm not going to test you a ton on step growth polymerization, but make sure you can recognize it when you see it, because we've already talked about that. We have an equation for that. We have an equation for linear. We don't have a great equation for chain yet, but we know it's shaped something like that. Questions? All right, that's important, but you need some hints to know that it's a living polymerization, because you can have an anionic polymerization that's not living, although it's not that common. Of course, you can have cationic polymerization that's not living as well. So you have to remember those basic mechanisms that we talked about, but living is a special case of anionic. And so you want to be able to recognize it when I give you some hints about the mechanism. And one of the hints about the mechanism is, in addition to the linear relationship between degree of polymerization and conversion, is this relationship for dispersity. So remember, we developed this dispersity for step growth polymerization, right? And for living anionic, of course, dispersity for any polymer is defined as m bar W over m bar N. But for living anionic, you start, well, where does this start? So what's the maximum dispersity that you can get for living anionic? So when X bar N is 1, and if X bar N is 1, what do you have? What is everything in the reaction? Monomer. So you start with monomer. And so what's the dispersity when you just start with monomer? Theoretically, it's 2, right? Although that doesn't make tons of sense. But dispersity starts at 2, and then as X bar N grows based on this math, what is the asymptote of dispersity as we increase X bar N? 1, right? So dispersity goes to 1 as X bar N increases. And we get that right from the math. So what does the plot of dispersity versus X bar N look like for living anionic polymerization? Starts high, flattens out. So it looks something like this, right? And we know the limit is dispersity 1. So from this equation, you should be able to tell me what the plot looks like. Or if I give you the plot and say the dispersity is trending to 1, you should say, that's a living polymerization, because that fits with the mathematics. Oh, hold on one sec. Let me get this note thing going. Oh, sorry about that. Hold on, I don't want to lose my place. All right, maybe it'll come back to me. Oh, no, it's not. I'm gonna make sure we're all secure. Well, let's see what happens now. Okay, apologies for that. Any questions? Yes.
So that disparity versus X bar N graph always starts at X bar N equals 1, because you can't have an X bar N of less than 1, right?
That's right. Degree of polymerization has to start at 1. Yeah. Other questions? So most of the problems, when we have equations that have to deal with chain transfer and Mayo-Walling equation and things like that, this generally will be free radical polymerization because that's what we've spent the most time on. You should know about the chemistry of that. You should know how termination by combination and termination by disproportionation work in free radical. And so most often the big questions with the big calculations will be on free radical. However, when you get to living polymerization, you're going to have to know that it's a living polymerization, and you're going to have to know some of the characteristics of that. So again, it's trying to read the problem and decode what's the polymerization mechanism, what's the polymer, right? I'll just say polystyrene. I won't necessarily draw out the repeat unit. I won't make it difficult, right? I'm not going to give you a repeat unit or a polymer that you've never heard of before. And so I'll give you some clues, but this is a exercise in good note keeping and trying to decode what I'm telling you. And if you haven't done the homework yet, there's only a couple problems, but the calculations can be a little bit long, especially if you don't stay organized. So make sure you take a look at that as soon as possible and get the homework turned in. Any questions or comments? All right. Oh, and so this is, since it's living polymerization, it never dies, right? And so I guess it's not really a zombie because zombies come back to life after they're dead. But you can terminate living polymers. So this is the living chain end. I'll just say this somehow later. And so you can terminate living polymers using termination agents. And that's a strategy that you'll learn in your advanced polymer synthesis courses. Okay, and you can read that to round out your study. All right, so we've covered most everything we need to cover in free radical, anionic, and cationic, and I have some notes. So I have these broken out, and we're not going to go through the notes again because they're repeats of the slides, but I am going to ask you some clicker questions so you can get out your clickers. We're in CD. So chain transfer to monomer is common in cationic polymerization. Okay, cationic polymerization, chain transfer to monomer. How will this affect Xn or X bar N? So you know the polymerization mechanism because I tell you that's kind of important. But anytime we have chain transfer to monomer, what is the process that's happening? We have a polymer with a growing chain end, right? So we have polymer. And we have a growing end, I'll put the star there. And then we have some sort of monomer, and chain transfer to monomer means that we have a terminated chain or a chain with a dead end, and we transfer our growing chain end then to the monomer. And so in the absence of chain transfer, we have what we have. That's what X bar N 0. And so how does X bar N compare to X bar N 0? We're making smaller molecular weight things. So X bar N is going to be less than X bar N 0. And so, whoop, I get the right thing. So the answer is A. You can ring in to make sure that I know you're here. Great. And this goes for any chain transfer to monomer. X bar N, which is the degree of polymerization in the presence of chain transfer, is always going to be less than X bar N 0, which is the degree of polymerization in the absence of chain transfer. That works for any mechanism. Same with, well, let's do some more questions, but same with the other types of chain transfer. And we'll ask you about how the molecular weight changes when you have other types of chain transfer. Yeah.
Yeah, what did you say about the molecular weight with this again?
So
Lower molecular weight?
yes, so that's exactly what. So A is the answer. And so if you look, X sub N, the degree of polymerization, which is what I'm asking you about, is less than X bar N 0. So X bar N 0, you know, is no chain transfer. And so what I'm really asking you about is compare the situation when you don't have chain transfer versus if you do have chain transfer. And when you have chain transfer to monomer, the molecular weight is always lower. Does that make sense?
Yes.
What about when you have chain transfer to polymer? How is XN affected? It's not. That is a special case, right? For any mechanism, if you take a growing chain in from one polymer and put it on another polymer, no change in your degree of polymerization. All right. Next clicker question. Of the choices below, which solvent would you choose for the cationic polymerization of styrene? Okay, cationic polymerization of styrene, got that? If you wanted fast rates of propagation. So what's special about ionic polymerization that's different than free radical? And we have cationic polymerization, which means that the growing chain end is a cation. What do we need for every cation? What do we need? Well, we need an electron donating group to stabilize that cation, but we also need an anion to balance that charge, right? Yes. That's right. So the concept is that a more polar solvent separates this pair because you always have a cation and an anion hanging around together in cationic polymerization. And so a more polar solvent will separate those ion pairs, which gives more space for the monomer to react with the cationic center and propagate. So that's the concept. Now, the question is, which solvent is more polar? Go ahead. That's right. So you can all ring in A. Make sure you're here. A is more polar, and so it gives a faster rate of propagation. And you should be able to figure that out because if you're like, well, I'm not quite sure what these solvents are, I'm just going to write it out. So, you know, how do I get 4 chlorines around carbon? And I know that carbon is going to be, well, I don't know why I'm putting a 4 there. Sorry. That would be a pretty awesome solvent. Okay. Okay. That's what it looks like. That doesn't look very polar because I know that that's sp3 tetrahedral carbon. And, you know, I'm not really sure what dichloromethane looks like, but sorry, I was going to draw a couple carbons there. But let's see if I draw it. I've got different dipoles in there. That's not symmetric. And so dichloromethane has to be more polar. And so you have to draw on some of your older chemistry knowledge to get to that point. But the real point of me asking you this question is that you know that cationic polymerization is dependent on solvent polarity. Yes?
If it asks what would be the best for anionic polymerization, would that be a different answer?
So we didn't necessarily talk about this ion pairing in anionic, but it would be similar. That if you separate the anion and cation in either anionic or cationic, the rate of propagation will go up. Yeah, yeah. There are some details of anionic that make that tricky because anionic turns out decomposes a lot of solvents. But the question remains, or the concept remains, for ionic polymerizations, if you separate the counter ion from the growing center, you get faster propagation. Yes?
Maybe a dumb question, but what if it was the CL is perpendicular to the other CL?
CL is perpendicular to
You
the
know, it's
other.
just one gigantic straight line, like CL is on top, like this.
Because it's tetrahedral, it doesn't matter.
That's right. Remember, it's a little pyramid or tetrahedral. So every spot is identical. So it doesn't matter, you know, where you put the atoms. I represented it like this, but this is actually the exact same as. Let me put an H there, CL. These are the same. Because there's no sidedness to the molecule. It's not chiral. anything like that. So if you go back and you're like, is Hickner right on that one? I'm not sure. Break out your organic chemistry model set. You could prove it to yourself. So build those two. You can turn one to look exactly like the other. Yeah. So it does draw on the prerequisites, right? You just have to remember those things. Good. All right. Any other questions or comments? All right, let's flip over to anionic because I have a couple questions there. I've already done that one. This is a really great one. I love this question. All right. Which graph best represents the relationship between degree of polymerization and extent of monomer conversion for a living anionic polymerization? I did you a big favor and I gave you the equation, but on the exam, I'm probably not going to give you the equation. You're going to have to go and find it. But I tell you it's living anionic. And so you know that this is the equation I'm looking for. And so I just march through all the different possibilities and say, okay, what could it be? So you can ring in. It's tempting, right? B kind of looks familiar. D looks familiar. I mean, we kind of talked about a plot in the shape of this, but that's not going to work for X bar N as a function of monomer conversion. We're never really decreasing molecular weight as we go to higher conversion. Now we probably don't have constant molecular weight as a function of conversion. That would just be a very special case of this one right here. So you can ring in. There we go. We got our numbers. And of course, just as we covered, since X bar N is linearly related to C, or we can just write that down, X bar N is proportional to C, means as C goes up, X bar N increases proportionally. So we don't exactly know what the slope is, right? We need to know some other things to know what the slope is, but this gives us a really characteristic curve for living polymerization. And so this is another really important concept that I'm going to emphasize in this class, is that you have an equation, and I'm going to ask you how one variable is related to the other variable. So when you change the initiator concentration by a factor of 2, what happens to m dot? Or if I change the concentration of monomer, what happens to the rate of polymerization? So not only plugging in values and solving is important, but being able to tell me the relationship between the two variables, either plotting them or saying, well, when I double this, I double that. We've practiced a couple of those problems. So make sure that you're savvy about looking at the equation and figuring out those relationships. And there's a couple things to practice on that. Questions or comments? All right. Next question. Which graph best represents the relationship between degree of polymerization and extent of monomer conversion for a radical polymerization? It feels like we're on the exact same question, but I did you a favor and outlined radical polymerization. So now you have some choices, right? What is he talking about? Radical polymerization, concentration, conversion. Remember, what type of polymerization is radical polymerization in general? Chain or addition. And then based on that, you should be able to select the right answer on what we talked about when we started. And so the right answer is X bar N increases quickly as a function of conversion and then sort of levels out, which means that you're getting the same molecular weight polymers at the end of the monomer conversion, and molecular weight increases quickly when you do chain polymerization, as we have discussed. Any questions on that? So this is key. If you have these two questions in a row, on the exam, you're like, this is the exact same problem. What is going on? And so this is where you have to read carefully and decode the situation from the information I give you in the problem, and make sure that you answer the question that I'm asking you. You know, sometimes your mind, you have a lot of concepts in there and you're like, well, I just jump right to this, but read that question very carefully and take a beat to make sure that you're answering the question in the way that I asked it. All right, another clicker question. We're clicker heavy today. Which plot shows an appropriate relationship between dispersity and percent monomer conversion for a living anionic polymerization? Notice that this equation doesn't have conversion in it. If you were looking for dispersity equals something as a function of C, you'll be disappointed because we don't have it in this section. But the concept that you need to know is that how is conversion and X bar N related for a living anionic polymerization? They're linearly related, right? So as conversion goes up, that means X bar N is going up. And so you have to make that connection on your own, and then you can answer the question based on the mathematics that we just wrote. And so you can ring in. So X bar N at low conversion, X bar N is small. Okay, and if X bar N is small, that second number there is larger than 1, or sorry, is closer to 1, right? And if at high conversion, X bar N is large, and when X bar N gets really big, this term will go away, and so the dispersity trends to 1. So what plot do we have where X bar N is changing, but we asymptote to 1? This one right here. I don't have any values on the y-axis. It's not perfect, that plot, but that is a relationship we're looking for, because we know that we trend to a constant, or we asymptote to a constant dispersity of 1 as X bar N goes up. And none of those other plots look very good. You know, even if we had a value on the y-axis for E, the dispersity is not constant as a function of conversion. We know it's not constant because of the plot. So that's the only plot where the mathematics fits the situation. But the key is that you need to know that percent monomer conversion is a code for what's happening with X bar N, because we're talking about living polymerization, so you know that relationship. And that's tricky. And so this is why we don't have tons of homework this week. Gives you some chance to practice, gives you some chance to absorb the material. And we have a couple days next week, including office hours and classes, for you to keep making those connections on your own, because that's what I'm looking for on the exam. Questions, comments? All right, we got tons of time. Here's another one. Let's just do this calculation all the way out. You make a polymer by living anionic polymerization and find at the end of the reaction, the dispersity was 1.01. Great. Living anionic polymerization and dispersity. This is the only equation that we have for the dispersity of a living anionic polymerization. There is no other choice. And so if this equals 1.01, what can we find based on that equation right there? X bar N, right? Does anyone know what that is? Here, I'm going to cheat so I know what it is. Yeah. It's okay. I made the question. I just can't remember the answer. So if you solve that equation, what is X bar N? So what's that? 100. I should have been able to do it by inspection because it's a nice round number. So first off, you need to be able to solve that equation. Take 2 or 3 minutes, make sure you do it the right way, and make sure you're able to mathematically solve that for X bar N. But I asked you, what is the molar mass of the repeat unit of the polymer? I didn't ask you X bar N. And so how do we get, what variable is molar mass of the repeat unit of the polymer? What variable is that? M naught. So I'm looking for M naught. And what information do I have to try and solve for M naught? What's one of our basic equations? Yes. Well, let's start with the easy one. Mn equals M naught times X bar N, right? It's really easy for me to remember this because I know molecular weight is big. I know what degree of polymerization is, how many monomers, and I know I have to multiply that monomer times the repeat unit molecular weight to get that. So I like to start with this, and then I can get to exactly what you said. M naught equals Mn over X bar N. And so all I have to think about is what's Mn for this polymer? Go ahead, you can say it. 15,000 grams per mole. And so I divide by 100, and my M0 is 150 grams per mole. So you don't want to put 15 in there because if you forget the K, it's going to look really funny. And you're like, I can't have an M0 of, 0.05, whatever it's going to be. So again, you can ring in. I think 150 is a choice. Yeah. All right, make sure you record your answer. And so we've now just run through that problem. So the point of these clicker questions is to warm you up to the type of questions I'm going to be asking you. Now that we have done some homeworks, now that we've learned some new concepts, we have a few different things going on. You'll have the practice test to help you as well. Now it's time to practice how I'm going to ask and how you're going to answer these questions. And remember to just make really good bookkeeping of what information you're given and what information you're looking for. And the equation sheet can help you because you don't have to memorize this. It's going to be right there for you. You just need to know that this is for living anionic. All right, questions, comments? All right, we are down to the last 2 things that you're going to need to know before the exam. And the first one of those things, which I know you all really enjoyed in organic chemistry, is stereochemistry and chirality. So yeah, I know it's great, huh? It's easier in polymers. Trust me, a lot easier in polymers. So stereochemistry and chirality in polymers is called tacticity. So if you have a chiral polymer, it's going to have tacticity. If you've got stereocenters in the polymer, it's going to have tacticity. And so you might not have heard tacticity before, but that's the word that's used in polymer science. The one nomenclature thing that we need to think about is we need to think about the backbone of the polymer and then how the functional groups are arranged in space. And I am a horrible 3-dimensional drawer, but I can draw solid wedges and dashed wedges. And so the way we do this in polymers is that the carbon-carbon backbone, these are addition polymers, right? They have carbon-carbon backbone, is in the plane of the board. So it's a zigzag because everything is tetrahedral, right? So it's all 109.5 bond angles as far as we know. But that planar zigzag, that carbon-carbon backbone is in the plane of the border, in the plane of the screen right here. So those carbons are laying on the surface. Now, the substituents, there will be one that has to point out. Of plane. And then you have to have one pointing in. And you can prove this to yourself when you go take your molecular modeling kit, put 4 carbons together and put some substituents on there and get all those carbon-carbon bonds in this planar zigzag. You can see substituents pointing out towards you and pointing back away from you. And this is how we represent chirality in polymers. And so I'll teach you some tricks for how to deal with this, because of course you could take that molecular model kit and you could mess it all up, right? You don't know where the substituents are going compared to the plane, but we're going to draw things very systematically. So it's really easy to figure out what the chirality is. All right. And well, we'll get to this. We'll keep going here. So most everything we're going to study is going to have 2 different substituents on one carbon and 2 hydrogens on the other carbon. Which is the head and which is the tail for these monomers? The head is what? Most substituted, right? So the head is going to have the chiral center. And then the tail, every single tail that we've studied is just CH2, right? All the monomers that we've studied pretty much are just like this. So you learned in organic chemistry, how many substituents do you need in order to get a chiral carbon? You need 4 different substituents. And this is the tricky part about polymers. It's easy to see that you have 1, 2, 3. Yeah, you have 2 substituents on this carbon, and you actually have 3, 4, because one side of the chain is different than the other side of the chain. That's tricky. The head is the chiral carbon. And the tail's doing nothing. The tail's just sitting there. It's got 2 hydrogens on it. You know, it's only 2 different substituents for the 2 different sides of the chain. So the tail is not chiral. And I'm going to introduce this concept today, and we're going to go over it again on Monday. Yes?
Would you explain why the substituent for the exotactic is not the same on both sides? Because when I understood on the first end, from the end.
We'll go through that. Hold that question 1 second. Okay. So this is how tactic structures are drawn in polymer science. So what does iso mean? Just as a prefix. Same, right? Isometric, you know, all that, a same or same side. And so these carbons, if you look here, carbon 1, carbon 2, remember we're only looking at the chiral carbons. And in this case, all chiral carbons are going to have 2 different substituents, because substituent 3 and 4 is one direction of the polymer chain and the other direction of the polymer chain. It turns out they're likely different. So you see that the Y's are all coming out at you, all solid triangles, and the X's are all going back in the board, which means the stereo configuration of each of those chiral carbons is exactly the same. They have the same stereochemistry, and so that means it's the same tacticity, which means isotactic. Same stereochemistry. At each chiral carbon. Notice it doesn't mean that every carbon is chiral in this polymer, right? Because every other carbon, the tail carbons, are not chiral. That's okay. We're just looking at the stereo centers as we march down the chain. Up, stereo center. What's the tacticity of that? Next stereo center, next stereo center, next stereo center. And we compare those stereo centers in order to figure out what the tacticity is. Yes?
How are 3 and 4 different substituents?
3 and 4.
The carbons, or like the substituents?
Sorry. Yeah, I was like, where's 3 and 4? So remember, for a chiral carbon, you learned in organic chemistry that you need 4 different substituents, right, to get chirality. And so that is still true for polymers. And so we have substituent 1, which is X, substituent 2, that's Y, substituent 3 is one direction in the polymer chain because that's connected to a carbon, right, next to it. Then substituent 4 is connected to a carbon going the other way. And in polymers, 3 and 4 are 2 different directions on the chain. And since they're different, that gives us 4 different substituents so we can have a chiral carbon. Yeah, it's a little esoteric because if you pick the exact center carbon in the perfect polymer chain, that one won't be chiral because each side of the chain will be the same, but that doesn't happen very often. And so we count that each carbon in the backbone like this, the 2 other bonds that it makes, because we always have 4 bonds to carbon, the 2 other bonds in the polymer chain are substituents 3 and 4, which qualifies that carbon now to be chiral. And notice this carbon, so this is a tail carbon right here. This guy is not chiral, and that's fine. Isotactic doesn't mean that every single carbon has a stereocenter. Isotactic means the stereocenters that you have in the chain all have the same tacticity, or all have the same chirality. So practice drawing that. Syndio is a funny prefix, and it means alternating. And so you see in our chiral carbon right here, Y is coming out at you. Next chiral center, we have a chiral carbon. Next chiral center, X is coming out of the board. Then Y is coming out of the board. Then X is coming out of the board. Then Y. So you have alternating stereochemistry. You could say alternating sides. You could say coming into and going out of the board. But you know what's really happening is that you have the opposite stereochemistry at each carbon. And so just remember what syndiotactic looks like in terms of alternating stereochemistry. And I'm going to teach you, if a polymer is all sort of coiled up, I'm going to teach you how to get substituents in the right places so you can visually inspect the polymer chain and make sure that it's isotactic or make sure it's syndiotactic. Because notice we've been drawing all the X and Y substituents up on the top of the chain, but we could rotate one of those carbons and things look a little bit different. We'll practice that later. All right, and atactic, A means not. So atactic means random stereochemical configurations or not isotactic and not syndiotactic. So if it's not exactly all the same, if it's not exactly alternating, if some are the same and some are different, you have atactic. There is no fourth choice. So you can't say, well, I've got 2 of the same stereochemistry followed by a third of a different. Then I've got 2 of the same followed by a third of the different. That is atactic in this class because it's not syndiotactic or isotactic. It has to be all the same or it has to be all alternating. Questions? Yes.
Can I say that? I mean, the atactic is.
You can say that it has random stereochemistry at each chiral carbon because these carbons are still chiral, right? But the stereochemistry changes as we go down the list. So it's random stereochemistry at each chiral carbon. Does that make sense? And the easiest, you know, it's hard to see randomness sometimes. You're like, oh, what's the pattern here? There's got to be a pattern. If it's not isotactic perfectly, and if it's not syndiotactic perfectly, it's atactic. So it's easy as the third option because, you know, the other patterns are exact. So I know this is new. This is very worthwhile to write this out, look at the book, get out your modeling kit. Notice that we're using solid lines in the backbone. So this is signaling that we have this planar zigzag that's all in the plane of the page. So the carbons are zigzagging up and down, which means the other substituents have to be pointed into and out of the board. And so this is worthwhile writing down, practicing this, looking at this. And I'll have a bunch of different examples because this is an important one to remember. And it's pretty easy to get it right when you know the tricks, and it's really hard to figure it out if you don't know how to rearrange some of the tacticity. Okay, well, we'll talk about how we make tactic polymers in the next slide. All right. So based on this, so notice we use X and Y for our monomer. So this monomer, of course, will go to those polymers that we just talked about. And so we've got monomers R1, R2. If we look at this, what if X and Y were the same? What if they were both chlorines? It wouldn't be a stereocenter because in one case, you have chlorine pointed back and you have chlorine pointed in front. And the same thing, right? You have chlorine pointed in back and chlorine pointed in front. So there is no isotactic versus syndiotactic difference because if X and Y are the same, if X and Y are the same, or R1 and R2, depending on how you like to draw your substituents, we don't have any tacticity. Because then we only have 3 different substituents on that carbon, right? R1 and R2 are the same, and then we have polymer going one way and polymer going the other way. That's only 3 different substituents, and you can't have a stereocenter on carbon with 3 different substituents. You have to have 4. So the clicker question is, you can get out your clickers, we're not done yet. Big Clicker Friday. Can you get tacticity with this monomer? You know, this should be like a 30-second question on the exam. Stop, take a beat. Okay, I remember what tacticity is. A, does this monomer work for addition polymerization? Because that's what we're talking about. This is the tail. This is the head. I've got carbon double bond. Yeah, that's a real monomer. Okay, I'm great. What do these groups mean? It means methyl group. And so the answer is we can't get tacticity with this monomer because R1 and R2 are exactly the same thing. They're both methyl groups in this case. So it's not like this has to be a 5-second question on the exam. You just don't want to blurt it out. You want to say, okay, tacticity, is this the right monomer? Do your mental checks. What does tacticity mean? Okay, X and Y or R1 and R2 are the same. No, I can't have tacticity. So, you know, take a couple seconds to make sure you check all the boxes and do your internal checks before just hammering the answer that comes to you. All right, what is the tacticity of this polymer? First of all, this is very funny looking, right? What's missing? Our other substituents, right? There are hydrogens on those other carbons because so far we only have 3 bonds to carbon. And this polymer has a stereocenter on every carbon for some reason. But the key is how do we think about deciding what the tacticity is? And notice that we have a substituent pointed down here and a substituent pointed up. And when we looked at the tacticity of all our stereocenters, all the substituents were pointing in one direction, right? So if I take this carbon or this methyl group and I rotate it up, because I get rotation around single and carbon bonds, I can do that, right? What is that arrow look like? Now I'm going to keep this one the same. I didn't do any rotation with that guy, I just kept it there. And if I have this methyl group that's pointing out at me and I rotate it up to the top of the chain, Where does that methyl group go? What does it look like? It's a dashed arrow. And now I've got hydrogens doing their own thing, right? They rotate along there. Now I have 2 chiral carbons. And what is the stereochemistry of those 2 carbons in relationship to each other? They're alternating, right? And I know that alternating is symbiotic. That is as hard as it gets, but that's hard. And it's hard if you just heard about it 1 minute and you're leaving class the next minute. So we're going to review this on Monday. Remember that to think about when you rotate around these carbon-carbon bonds, what happens to the substituents and why? Get out your molecular modeling kit, and I'll see you on Monday. Don't forget to turn in your homework.